So hi everybody, my name is Mario Daigle. I do product management with Interset from Canada. Just like Stefan this morning, I'm sorry. We'd like to apologize. So I'm going to do a talk on machine learning and the kinds of the types of different machine learning that can apply to different types of problems in the context of cybersecurity. This is a pretty nuts and bolts kind of a presentation. I try to keep it very concrete so we can take the information and do something with it. So if I'm successful with this talk, at the end of it, you'll understand the difference between two very common types of machine learning that we see in cybersecurity and the kinds of problems that they can reasonably solve. Okay. So there's some stuff before I get going, so let everybody know. Social media. Remember to review Micro Focus software. I'm sure you see this on every presentation that you attend. All right, here we go. Disclaimer, again, boilerplate. Okay, so who knows what the Gartner hype cycle is? Gartner hype cycle? Yes, no? Okay, so the Gartner hype cycle I think is a really cool concept because what it does is it helps us understand emerging technologies and how they manifest and related to expectations and actual use cases that they can solve. And so part of the hype cycle, when a new technology becomes available, there's an inflated set of expectations. So it's like a big spike. So all of a sudden something comes out and everyone expects that it's going to do a whole lot of things. And then after it hits that peak, it falls off in what we call the trough of disillusionment. And the trough of disillusionment is when people realize that the technology isn't going to solve the problems in the same way that they expected, and so people kind of give up on it. Literally, that's kind of what it is. It's generally followed by what we call a plateau of productivity, which is kind of when expectations become more realistic about what it can and can't do, and then use cases become reasonable, where the technology can solve it. So why does this happen? It usually happens because there's a whole lot of marketing that occurs with a given technology, and so from that marketing, people expect the results that they're promised by the marketing. So that's what happened in the context of machine learning specifically. So in 2007, like you saw before, it was right at the top of the hype cycle, and it just dropped off in the trough of disillusionment. That's kind of where machine learning was. So the good news is, in terms of understanding machine learning and what it can actually do, you don't need to be a data scientist, you don't need to be a data architect to understand the basic concepts of how machine learning is used to be able to make good decisions. You just need to understand the basic approaches, how they work logically, and then you'll get a sense for the kinds of problems that they can solve. So that's what I'm going to try to talk about today. Okay, so I'm going to talk about human intelligence to start, kind of how humans deal with inputs and outputs and how we learn. So I'll use this basic framework to start with. But before I talk about this, I'm going to tell you a little personal story. So when I was a little boy, I'm going to say about 7 or 8, me and my friend Luke became infatuated with these little army guys with parachutes. You remember those guys? You'd kind of wrap them up, tie them up, and you'd throw them in the air, and they'd come gliding down. I see some nodding heads. So me and my friend Luke, we played with those for hours and hours. We love those things. We had like a whole bunch of them, and we just played with them, and we were little, and we were not very smart, and so we really wanted to be those guys. So we went around, gentleman in the back knows exactly where I'm going. So we went around the house looking for something that could behave like a parachute. I really wanted to be that hero falling gently down from the sky and landing heroically down on the ground. I was desperate to live that experience. So I remember going around the house looking for something that could act as a parachute, and I came across these big garbage bags. You know, the big ones that, you know. And so I got a garbage bag, I climbed up on top of our house. Thankfully, it was a bungalow, so 1 story, not too high. I opened it up, I filled it with air, and I jumped off. Now, I vividly remember the moment when I realized that my dreams were not going to come true. I was not going to be a hero. I was going to be quite the opposite. So there's a memory input there. So human intelligence, sensing and perception, right? There's the inputs and the outputs, right? If we take this and sort of break it down, we have knowledge and we have memories. I have a very vivid memory that I described to you. In fact, I can go even further. I can still picture the sky when it happened. It was blue sky, beautiful day. There was some white fluffy clouds, not too many. It was warm. It was like a perfect summer day in eastern New Brunswick, just east of Maine, like way on the east coast. I can still picture the sky. It's implanted in my mind. And I can still feel the ground when it met me as I went to the ground, when I realized that my experiment was not going to work. So we have knowledge, we have memories, and then we make decisions and we make inferences. I have successfully avoided jumping off a house with a garbage bag ever since. So now I've made better decisions. And I can also infer as a human being that if I jump off any tall structure without the right gear, something bad's going to happen. So humans have this unique ability to infer, something that we've learned from context A and apply it to context B. That's very specific to humans in terms of how we learn. So hopefully, we go through this process continuously as humans, and we learn. So let's take this learning concept and break it down one level deeper. So we learn in two basic ways. We learn by example, and then we learn through direct observation. So I learned that lesson through very direct observation. I fell to the ground, I experienced that pain, I experienced the bruised ego and the shattered, the shattered dreams, and I experienced that very directly. What I failed to mention is that my friend Luke, he convinced me to go first. So he also learned a very valuable lesson, but he learned by example instead of through observation. Now, to my knowledge, he has also successfully avoided, ever since that day, jumping off a house with a garbage bag. So good for him. He was able to learn that same lesson, but he didn't have to go through the same humiliation and a bit of physical pain to learn that lesson. So we learn by example, and we learn by observations. AI is not that different. AI, or learning in terms of how machines execute, is not that different. We have inputs and we have outputs. Inputs are the kinds of technologies that we use on a regular basis, but now become kind of pervasive, right? NLP, speech recognition, all these things. When you talk to your phone and ask it for directions to get somewhere, it uses a lot of these technologies, and it ends up giving you an output. You get navigation, you know where you're going. Very, very useful applications. So you can take the same framework and apply it to AI. So the same concepts apply. We have knowledge and memories, but in case of machines, knowledge and memories are represented by databases, right? Data holdings. So these are databases with information that we take for granted, but they're just getting bigger and bigger and bigger. And then there's these applications that use the information to make decisions. A very simple example: when you apply for a loan, the application will query a number of different systems, come up with a risk score for whether or not you're worth the risk, and then it'll come up with a decision. So it's a decision that the AI makes, and the output is you get approved for a loan in a matter of seconds or minutes, instead of having to go through a bank like we used to do 30, 40 years ago, and have to wait a long time, right? So the same concepts are generally applicable. So let's take the learning side in the context of AI and break it down. So there are two very specific types of machine learning: supervised learning and unsupervised learning. So I'm going to start by talking about supervised learning. So we have an image of a gentleman here, and what emotion is he displaying? I think you'd all agree he looks pretty happy. Perhaps he just ordered a beer and it got served to him. Why do we know he's happy? Well, as humans, we don't even have to break it apart. We just know, and there's an intuition that happens because our brains automatically takes the attributes of the image, and we kind of make up our minds right away. A machine doesn't have that same kind of intuition, but the machine can decompose the image into its constituents, its attributes, and then from that, it can actually classify the emotion of the person. Classify when he's happy, another one he's sad, another one he's angry. My bill's a little off there. So in the context of supervised machine learning, it's all learned by example. So just like my friend Luke the machine has to see examples of what it's looking for. So if you feed the machine millions of examples of a face and you tell it these faces are happy, the algorithms are going to figure out the attributes that are common across those images and learn to discover them on new images that are fed to them that are not classified. And that's how machine learning can start to classify images. Like when you go to Google and there's automated classifications happening, that's how it's doing it. Tons of images have been fed into the system. It's learned, the algorithms have learned what makes a face happy, sad, or angry. And then when it sees new images that haven't been classified, it's able to take what it's seen, use its knowledge of the attributes that are common for happy faces or other images, and then apply a classification. So supervised machine learning kind of works that way. But unsupervised learning is different. Unsupervised learning doesn't judge, doesn't classify. Unsupervised learning will identify what is different in a given environment. So unsupervised learning, as you feed it data, it learns what's normal. It just gets used to what's normal and what it can expect. It's not going to tell you if it's good or bad. It's just going to tell you if it's the same as what it expects or if it's different. So we kind of think about that as context, right? So as data gets fed into the system, it learns. So if I'm, for example, if I'm being monitored by an unsupervised learning system, it's going to just learn what I normally do. What time do I normally come in? Which hours of the day do I typically work? What applications are usually running on my machine? What file shares do I typically connect to? Do I ever fail my logins? Am I logging on the same way? Am I logging on using Kerberos, or am I doing RDP? All these things. Basically, the machine will just learn what's normal for me and then identify when it's abnormal. So to take an example from our previous friend here, right? We're asking a very different question. It's a different kind of question. So in this case, we're not asking if he's happy, sad, or angry. We're not asking for the machine to classify what it's seeing. We're asking if he's behaving normally. It's just a very different question. So is it normal for him to wear bike clothing, mess around with props, or any of these other things? In an unsupervised learning scenario, we can say that the machine has seen all of these things happen, but it's never seen him drink coffee from a coffee shop. So it'll just say, bing, that's different. Not saying it's bad, it's just different. So that approach cannot answer if it's good or bad. It can only answer if it's different. It's a very important distinction to make when thinking about cybersecurity. So let's actually take these concepts now and apply them to cybersecurity. So supervised learning is great for an application like malware because we have lots of examples of malware, tons, millions. You can feed a machine lots of examples of malware and it can learn the characteristics of what malware is and over time get better at identifying new strands of malware. So supervised learning is the kind of technique that's being used generally with malware tools, and that's how it executes. You give it examples, it learns what's common about those things, and then identifies when a new file comes in whether it's malware or not. But you have to tell the machine what you're looking for, and that's the key point to take away from supervised learning. You've got to be able to show a machine an example. So for malware, that's fine, but what about when you're dealing with trying to find insider threats? So you're trying to find people who are leaving your company, giving their notice, and taking all of their customer contacts, private plans, intellectual property, whatever. If you're looking for that kind of behavior, if you're looking for an advanced attacker, think of an APT, think of a nation state who's been able to infiltrate your network through spear phishing expeditions, social engineering, or other types of approaches, and has been able to find persistence somewhere. So they've got control of a machine, they've got credentials, they've compromised an account, and now they're inside. When they're inside, the account they're using has access to content. So it's not going to necessarily break a rule, it's not going to break a policy, it's going to just execute what it's entitled to do. How do you find that information, right? How do you determine if someone working at midnight, if someone's sending a bunch of data via email, or looking at specific data, how do you determine if these things are malicious or benign? Well, the answer is the machine can't tell you if it's malicious or benign. But the machine can tell you if it's abnormal. So think about this one as an example. Think about cmd.exe, or any process that's running on a workstation. If you're trying to find malicious ones, well, you're gonna have to scroll through a bunch of legitimate ones before you find a malicious one. It's like literally looking for a needle in a haystack. But if you've got a machine that's actually profiling every single workstation and understanding that this particular machine that sits in HR never has PowerShell run on it, but all of a sudden it does, you want to be alerted. That's the kind of use case that unsupervised machine learning can do. It's not going to tell you it's bad. So people that tell you it's going to give you 0 false positives, they're lying. It can't. But it can tell you if it's different. So your threat hunters that are trying to find these threats that are really, really hard to find, almost impossible, can get legitimate high-value clues, high-value leads from this kind of approach. And that's the difference. The idea is that insider threat or outside attackers, like APTs, are going to behave differently than their peers or than they have been behaving historically as they start to prepare for the exfiltration. That's how you want to catch them, and this is the kind of technology that can help your threat hunters actually do that, and that's the difference. So those concepts are important because when you walk down the rows at RSA or Black Hat, you see everyone has AI and machine learning, and they're going to find all your threats, and it's going to make you coffee in the morning, and the world's going to be wonderful. That's not true, and we know that's not true. So understanding these concepts can help you screen out certain conversations and guide you to asking the right questions. So here's a few questions to help you try to find the right tool for the job based on your use case. So it's not rocket science, not data science. It's actually not that difficult. So number one, and this comes from just experience and kind of engaging with customers where they're applying the technology to solve the right kind of use case. So define your needs, right? What use case are you trying to solve? It all starts from the use case. What outcome do you want to achieve? Start with that. Demand vendor clarity is my favorite one, so important, and evaluate the right thing. So let's take these and break them down a little bit. So define your needs. So what is your security operations maturity? If you're not collecting logs already, then don't let someone try to sell you an AI solution or a machine learning solution. Start with log collection. Just work sequentially in a logical, pragmatic way. It always works better that way. Understand and identify and document the things that you need to protect. If it's PII, if it's corporate IP, if it's design plans, if it's software, whatever the case may be, make sure you understand exactly what you're trying to protect, and it'll help guide you towards identifying the right outcomes that you're looking for. And what gaps do you have, and what are you trying to fill? That's number one. Demand vendor clarity, my favorite one. Refuse to hear jargon. I was presenting a similar but slightly different talk than this up in Ottawa this past winter, and the presenter just in front of me literally said, what you need to know is you bring in your appliance, you plug it in, it'll find all your threats, that's all you need to know. And I was just kind of horrified, like it paints the vendor community in such a bad light. It's such inflated expectations, it's just not right. So refuse to hear jargon. Anyone who tries to obfuscate what they do, be suspicious. Use a whiteboard. Think about the outcomes that you're looking for and anticipate what you'll do with the outcomes. Just write it out from left to right. Some of our best engagements come with these kinds of approaches. And practice it. Imagine if you've got the outcome you're looking for, what are the next steps and what do they look like? Do you have the steps in place? Do you have a sense for what it would look like? And then evaluate the right things. Do you have the data required to protect the things that you know you need to protect? Are you covering the right assets, right? Are you able to integrate with other systems so that your SOC teams, your threat hunters, are actually able to use the tools they typically use, right? If you've got to force them to use a new set of tools, guess what? They're not fans of that, right? It's going to slow things down. So make sure you can integrate, make sure it's going to plug into your system and play well with the ecosystem. And do you have the right security team makeups and skills? Do you have threat hunters on staff? Or do you have like level 1 incident responders, right? Those are the kind of questions that can help you determine if this kind of technology is something that that is kind of in your wheelhouse. So So we are Interset. I think Stefan, if everyone was there this morning, Stefan gave you an idea of what we do. We're an unsupervised machine learning technology. Our focus is on taking billions of logs of data and turning it into a small number of high quality leads. If you think about specific use cases where we usually get involved, usually it's insider threat or outside attacks. We notoriously find red team attacks when we have the right data, which is pretty exciting. So if you don't know what red teams are, they're ethical hackers who infiltrate their company's network to test the resiliency and the ability for the company to detect them. So we do a lot of that kind of stuff because we have models that identify unusual behaviors. We don't classify it, we just identify unusual behaviors and help give threat hunters the clues for what they need to find. So, usually I end here, but I added this just to illustrate the concept in a little more detail. So just to highlight the difference for what our approach is like compared to the traditional approach. So this comes from Carnegie Mellon Insider Threat program. And it's basically a pattern to try to find someone who's about to leave and take information with them. So this kind of reads like, if there's a set of emails that are going from inside to outside, and the amount of data being transferred is more than a specific threshold, then send an alert. So in a large organization, it usually looks like this. If you imagine the green line being sort of legitimate, normal behavior for your users in terms of that specific behavior. So maybe based on just analyzing the data, the mean for the amount of data being transferred via email when data gets transferred by email is, say, about 40 megabytes. So you say, well, I want to try to not look at most of it. I want to just see the top end. Then I only want to see the ones that are more than 50. The challenge with that, when you apply it to a population, is that, as you can see, all legitimate activity under the green line they're false positives. They're effectively benign behaviors that you'll be forced to look through to try to find what's under the red line, which is, in theory, your malicious behavior. The other challenge is there are some malicious behaviors to the left of the line. So applying a threshold across a population is very ineffective because some people's jobs require them to send data out. Maybe they're doing M&A, maybe they're doing financial records, but whatever the case may be, part of their job is they've got to send data outside to vendors, to partners, or whatever the case may be. In our world, it looks different. It looks a bit more like this, right? So in our world, we let the machines do what machines are really good at doing, which is basically build a set of metrics for a given behavior and identify when it's unusual. So if you let a machine just calculate whenever someone's sending data from inside to outside and just build up those metrics, it's just going to, as data comes in, it's going to query the data and it's going to build a table to understand the mean and the distribution of that behavior. So it'll know for Billy Dennis, who's the user in this screen cap, that the amount of data typically being sent by this specific person is very small. So this specific person almost never sends data outside the organization, right? But in this case, what's observed, even though it's less than 50, which was the threshold that we saw in the previous example, this is very unusual for this person. So understanding normal for each individual user is something that machines can do really, really well, really, really quickly. Humans could also do it. You could do a full analysis to figure out what's normal for Billy Dennis, but could you do it for 20,000 people? Really, really hard to do. Machines can do it. They can do it at scale. They can do it fast. That's the difference. Machines can take very specific, narrow use cases, and through unsupervised machine learning, on its own, learn what normal is for a given behavior and highlight when it's abnormal. So the previous example, that use case, the spirit of that use case is addressed but differently using this kind of technology. So in our world, this ends up pushing the risk of that user up, which gives a lead to the threat hunter so they can go and investigate. They can then go see what data has been moved out, does the person have a new job that requires them to send data out, and basically validate that it's a threat or it's benign. So these are the kinds of examples in how Interset and our technology is different than supervised learning approaches, which are typically found in the space. I'm doing another talk right after this, I think, at 4 o'clock It's sort of a continuation. There's a little bit of the same content, but it talks about human-machine teaming. And then there's another session tomorrow at 9:20 a.m. Using machine learning to solve real-world security problems. Paul, is that you doing that session tomorrow? My friend Paul Reed, who's sitting over there, he'll be presenting that. He's got some great stories. He's an amazing threat hunter. He's found some amazing stuff. So if you're interested in hearing real-world examples for how this actually manifests, it's a great session. I highly recommend it. And there's other demos, and of course, you can come and talk to me after this session if you have any questions. Another reminder to review the software for Gartner. And that's it. Thank you very much. If you have any questions, feel free. Any questions at all? Yep.
This is behavior-based solutions have been around for a while, and to learn them, the different models, you have to have some kind of burn-in period.
Yep. Yes.
An example of one of the first ones I knew was Bill Hancock in the 80s, where he had his network pod.
Yeah.
I used the place I was. It worked great until somebody started distributing software and thought a virus was in it and killed it.
Right.
So in regards to learning some of the
Yep.
outliers or anomalies,
Mhm.
you have what I would call a
Burn-in period.
mode or whatever, and how long does this take to learn your environment?
Yeah, so it's a good question. We typically talk about 30 days of data as sort of a kind of the gold standard, right? It can be less in the case of some models or more in the case of other models, but generally 30 days is a good starting point. So you're right. Unsupervised machine learning needs data to learn. If it doesn't have data to learn, it doesn't know if it should fire off and learn or not. In our case, it's got its own confidence level, so if it doesn't have enough data, it's not enough data to build a baseline, it's not going to fire any alerts. What we typically do with customers is we'll try to get historical data, so we can do a batch ingest of 30 days of past data, so that from day one, we've actually got baselines built up, and then we can start to analyze. In terms of the kinds of models that learn more quickly, is just about density of data. So if you're analyzing data on a computer, on your endpoint, and you're trying to profile what processes are usually running, or processes, is Canadian process? Yeah. A boot. Yeah, it's a boot the process. So in terms of the workstation data processes, dense data, it'll probably take a few days for it to build up baselines. But other models like unusual day of week, we have models that look for whether or not someone's working on Sundays. They've never worked on Sundays before, then for sure we need more than a week's data, because only one day, one example of Sunday is not enough to build a baseline. So
would it be fair to say that it depends on the functionality of your environment? Like if you have a billing system, you should go at least through 1 or 2 billing, or if you have a manufacturing, the process it goes through, is that would actually help model how you would collect the data?
So how we collect the data, are you talking about like the actual connection to get the data, or it depends on the characteristics?
Connection and to build a model. Does it also depend on what you're doing?
Well, our models are out of the box. So all of our models are in the box. They just execute. So if you feed it Active Directory data, it's going to identify login successes, login failures. It's going to identify how you're logging in, where you're logging into, how frequently, and all that kind of stuff. So we have between like 50 and 150 models on Active Directory, depending on how the environment's instrumented. And then that's generally fairly dense data. So within a couple of weeks, you'll have some pretty good baselines. But it all depends on the characteristics of the data. So for example, one customer wanted us to do badge data for laboratories. We don't have that as a set of models. Like we don't necessarily support badge access data out of the box, but we mapped it to another set of models on what we have a resource models, so basically looking for accesses to something. But in case of badging in a route, usually it's not per hour, right? Like you'd usually badge in once per day or a few times per day. So then that will take a longer burning period to sort of normalize. We call that the models would converge. So the models are in the box, and then they converge once there's enough data inside the system for the metrics to have a high enough confidence score to start emitting anomalies. Yeah. All right, problem. Yes, sir.
Any thoughts on false data injection?
Or pollution, or baseline pollution. Yes. Yeah, that's another good question too. we have a couple of ways that we deal with that. One is the sheer number of models that we have means that you'd have to pollute a lot of baselines to be able to really get out of the limelight, I think. The other thing is we do peer analysis. So we use clustering models to group users together based on a common behavior dimension. So the best example I can think of is if you've got file shares on your network, so people are accessing file shares, we'll create clusters of people based on groups that are accessing generally the same set of file shares. Once we've got those groups, we're going to take behaviors that we measure and compare to their historical baselines, and we'll compare them to the average of their peers as well. So it provides another dimension of data to evaluate anomalies. So there's a few different ways that we can sort of identify that. But the reality is data is data. If you know exactly the models that you've got that are in the system, and you pollute, 150 different baselines, in theory, you could, pollute the baselines. Well, so I would tell you that for insider threat or APTs, I'd say that it's impossible to use supervised learning because you'd have to provide an example of insider threat or what you want to find. So if you think about a human in terms of stealing data, you'd have to be able to provide a snapshot of how you think the user is going to behave kind of in a specific span of time so that the machine's going to look for that pattern of behavior. But if the behavior doesn't match that pattern, then you're not going to find them. That's the challenge with insider threat. There's too many, there's an infinite variety of insider threats. And so a supervised approach, the challenge is you have to tell the machine what you're looking for exactly. An unsupervised approach will just let the machine identify when something's different, and then you apply human intuition to provide the judgment. That's kind of the difference between the two that I see. Does that make sense?
So something a little bit more esoteric. Do you normally see this done at the core, in the core data centers, or do you actually do inferencing out at the edge? Do you have edge-based use cases?
Sorry, I'm not sure what you mean.
All right. So, in many instances today, we have a lot more devices that we're dealing with.
Yep.
With a lot
Oh,
of
I see. Got it.
edge,
Yeah.
Our edge or near edge.
Yeah.
And I'm just curious as to the deployment model.
Oh, yeah. So we do a bit of both.
All right.
All right, yeah, that's right. So we do a bit of both, but primarily we're inside. But we are increasingly being asked to address use cases outside. We have NetFlow models, which gets close to kind of what you're asking about, and we do both north, south, and east, west. We generally, in terms of kind of what we do well, think of insider threat, think of APTs. Usually you're looking at a company and a company trying to find these kinds of threats. So that's typically where we land. But we keep being asked by telcos and other organizations that are looking to try to identify proactively malicious servers out there on the web. So if you think about NetFlow models and looking for unusual transactions or unusual connections between servers out there, then those are use cases that we're being asked to address. And we've got some pilots happening to try to address some of those use cases.
And to be a little bit more elaborate, some of these use cases that tend to be out at the edge, could be anything from injecting false data or threats like in the case of a power grid.
Yep.
There's esoteric things that you can do, but I'm looking for more sophisticated things that look at anomalies.
Yep.
Beyond the classic use cases.
So one of the models we've built that if you go to talk by Stefan, he'll probably call out. He loves to show it. It's a model on NetFlow which does two things. It'll classify whether or not it believes there's a human at the keyboard. It does that by figuring out from a NetFlow perspective what are the patterns of communication from the endpoint outside. As you can imagine, when the machine is dormant, even if it's active, the chatter is going to be very small and it's going to be pretty consistent and monotone. Conversely, if there's a human there, the machine is going to be accessing applications, websites, doing emails, those sorts of things. There's going to be a lot more variation. So the model will classify whether it thinks there's a human at the keyboard. And then, once it knows that, if there's no human at the keyboard, based on its classification model, it'll identify if there's unusual protocol behaviors happening. So for example, if there's email activity, and I forget the port number, and it's SMTP type of activity, and there's no human at the keyboard, it'll flag up an anomaly. Yeah, so it's, yeah, so we have some models in that area as well. Yeah.
So maybe just help me think about it. So in a typical SOC, you have like, you have your tier 1, tier 2, tier
Yeah.
3 analysts.
Yeah.
Will you assign a set of analysts just to UVA? Or is this like a
Yeah.
security shop, or is this something
That-
that's just a tier 1?
That's a great question. I love that question because, and Paul, feel free to jump in if you want to. This typically ends up being a threat hunter's tool, right? Because really what you're looking for is you want to give the leads to your L3 analysts, your high-end analysts, who are going to go and explore whether or not there's a potential compromised account, an external attacker has actually got persistence, or potential insider threat. Typically, it's not a level 1 analyst because level 1, so this requires interpretation, right? It's not just an incident with an automated response. It could be in some cases when it's really obvious. Like for example, we had this customer who we had failed login, unusual amount of failed logins. It was like 16,000 failed logins in like 5 minutes. So yeah, you can shut that one down. There's something completely wrong there, right? So you could automate that, but by and large, when you're looking for insider threat, there's a level of governance that you have to apply to that, right? So typically insider threat programs are handled a little bit differently than sort of standard incident response. Yeah, but it's a really good question. Yeah. Yes, sir.
On these turnkey solutions that you said to watch out for, did they say just turn it on, we'll start collecting logs and watch everything, and you just have to trust us? Is that it?
Yeah, so the one that I saw was up in Ottawa. He literally just said, all you need to know is you plug in the appliance, start collecting logs, it'll find all your threats. Those were the words. And then when I went up to present, he left. Because I was kind of interested to hear kind of his perspective on my stuff. But that's kind of what he said. Now, I'm not saying everyone says that, right? But in this particular case, I thought that was a really good example of what to be suspicious about, if nothing else. Any other questions? Great. Thanks very much. Enjoy the rest of the show.